we have to discuss the device named as solenoid and toroid. This one is the device with the help of which one can produce the uniform magnetic field. Now, first of all, the solenoid. Solenoid, that is a wounded wire in the helical shape, that is called solenoid. But each and every turn, that is insulated with respect to each other. So when the current is passed through that particular wounded wire, which one is in the helical shape, so due to these insulated turns, the current that will flow in the helical form. When these wounds are very close to each other, then we can consider each turn almost as a circular loop. So magnetic field inside the solenoid along the axis, that will be uniform one. And if we consider a long solenoid, then inside it at any point one can consider the magnetic field, that is uniform one. Now see, this one is the cross section of the short solenoid, and see here the turns of the solenoid are represented here as per our sign convention. Say, if we consider the turn which one is coming out, then at that particular place we have to represent that particular turn by dot in the circle, which represent the outward direction. And if the turn is going inside, then we have to represent it by cross. So direction of the current, that will be also as per the direction of the wounded turns. Now all these are turns. See, now if the current is flowing through these turns, then the magnetic field produced by this current carrying turns, that will be as shown in the figure. But see here, the interesting thing, that is this one. Suppose we consider these two consecutive turns. Then see here, between these two turns, if we think about the magnetic field, then for this first turn, say the magnetic field, that is loop form, and here see this particular arrow. For this second one, see this particular arrow. So here between these two turns, you can observe this thing, the magnetic field, that is mutually opposite. So it will cancel the effect of each other. It will cancel the effect of each other. So here outside this, when solenoid is a short one, no doubt, outside this one, the direction of the magnetic field for these consecutive turns, that is same one. So if we take the vector summation of all these, then resultant magnetic field, that will be in the loop form as shown in this figure. But if we consider the solenoid that is infinitely long, then in that particular case, outside this one, the magnetic field, that will be zero. Clear to all of you this particular thing? So here figure represent the magnetic field lines of the finite solenoid. Okay. Now see here on the axis of the solenoid. Here we consider a point P. Then see the magnetic field line, that is a straight line, which suggests this thing for the finite solenoid. At point P, which one is on the axis of the solenoid, the magnetic field that is uniform one. But if we consider the solenoid that is infinitely long, then at any point inside it, the magnetic field will be uniform one, because very close to the axis, if we see these particular field lines for the finite solenoid, then also you can observe this thing are almost parallel, very close to each other. So for long solenoid, you will get the uniform magnetic field. Clear to all of you? Now, for finite solenoid outside it, here if we consider the point Q, then we can observe this thing outside the magnetic field for each turn, that is in the same direction. See here the loops are anti-clockwise. So outside this one, the direction of the magnetic field due to each turn, that will be same one. So resultant magnetic field outside, that is the vector summation of all these, and that will be as shown in this figure in the loop form. But if we take infinitely long solenoid, then in that particular case, see here, between these two turns, the magnetic field that is opposite, so it will cancel the effect of each other. And due to infinite long, when we consider this particular loop formed, that is with infinite length, then we can consider outside this one, the magnetic field that is almost zero. Clear to all of you? Now the equation for magnetic field at any point inside the long solenoid. Here long solenoid means we have to consider the length of the solenoid that is too much large compared to the radius of the solenoid. Now see here, suppose as shown in this figure, this one is the long solenoid. Its cross section is represented here. From upper side, the turns are coming out, and from lower side, the turns are going inside of the plane of the paper. So here on upper side, the turns are represented by dots, and at lower side, the turns are represented by cross. Okay. So as the turns are there, if you pass the current, then current will flow in the same direction. From upper side, the current will come out. From lower side, it will go inside. Then again from upper side, it will come out. From lower side, it will go inside. Now, each turn that behave like a circular ring, then the magnetic field that will be along the axis. So if we place the fingers in the direction of the current, then thumb will point the direction of magnetic field. So in our case, from upper side, the current is coming out, means fingers are adjusted as you see. So thumb is pointing this particular direction. So magnetic field inside the solenoid is represented on right side direction. Clear to all of you? Now for long solenoid, inside it at any point, the magnetic field that is uniform one. So field lines are represented parallel to each other and with straight lines. Now to find out the magnetic field at any point, we have to apply the Ampere's circuital law. Clear up to this? Now, first of all, here we have to consider Amperian loop. So, as shown in the figure, consider the rectangular Amperian loop A, B, C, D, A. Okay. Now see here, if we apply Ampere's circuital law to this particular Amperian loop, This Amperian loop that is with length equal to L. Half portion of this loop that is outside the solenoid, half that is inside the solenoid. Now see, Ampere circuital law, that is integration B dot dl, that is mu 0 sigma I. Okay. And here suppose number of turns per unit length of the solenoid, that is a small n. Now this integration B dot dl. So we have to carry out the integration over the entire loop. Here we can use the integration rule in which we will carry out this particular integration by parts. So first think about integration B dot dl on different part of this particular loop. So we can take this integration first A to B, then take integration of B on B to C, then take integration of magnetic field B on C to D, then take the integration of the magnetic field B on D to A. So if we take the summation of all these integrations, then we will get the resultant integration of magnetic field along this particular closed loop. So this is integration by parts. So integration B dot dl, that is integration A to B, B dot dl, integration B to C, B dot dl, plus integration C to D, B dot dl, plus integration D to A, B dot dl. Now let's solve these integrations one by one. Suppose first we think about the integration B dot dl for limit A to B, means on this particular line. Now see here, half portion that is outside the solenoid. Outside the solenoid, magnetic field that is 0. So integration B dot dl for this half portion of the line, that will be equal to 0. Then after, if you think about the line which is inside the solenoid, now for that, on the line, if you consider infinitesimal small element, that is dl. Now magnetic field that is in horizontal direction. So dl and B both are perpendicular on this particular line. And therefore, the dot product of B and dl, that will come to 0. So resultantly, we can say integration of B dot dl along AB, that will be 0. Clear to all of you? Now integration B to C, B dot dl. So for line B to C, the line element dl and magnetic field B both are in the same direction. So angle between those two, that is 0. So B dot dl, that is B dl cos theta, theta is 0, so cos 0. So we can represent this integration B to C, B dot dl as integration B to C, B dl cos 0. Then after, integration C to D, B dot dl. So as we discussed, the integration B dot dl for line AB. In the same way, for line CD, it will be equal to 0. Then after integration B dot dl from D to A. So see this D to A line, that is outside the solenoid, and outside the solenoid magnetic field, that is 0. So this entire integration B dot dl will be 0. So finally, you will get integration B dot dl, that is, this cos 0 is 1, B is uniform 1, so take it outside the integration. So B integration dl. Now, dl, starting from B up to C, then that will give you the resultant length of this BC side, and that is equal to L. So we can write B integration dl, that is BL. Okay. Now we have to solve this right hand side. Now here, suppose the current flowing through the solenoid, that is I. It implies that through each turn, the current flowing, that is I. Now, mu 0 sigma I. Sigma I, that is the net current enclosed by the Amperian loop, or we can say net current passing through the Amperian loop. So here, number of turns per unit length is small n. So here the Amperian loop considered, that is with length equal to L. So total number of turns accommodated in the length L, that is NL. And through each turn, when the current flowing, that is I, it implies that through NL number of turns, the total current, that is NLI. So this sigma I, net current flowing through the Amperian loop, that is NLI. Now compare these two. So we can write integration B dot dl, which is equal to mu 0 sigma I, integration B dot dl over the Amperian loop, that is BL, and mu 0 sigma I, that is mu 0 NLI. LL cancelled. So B, that is equal to mu 0 NI. And here see this equation, mu 0, that is constant one, and that is number of turns per unit length of the solenoid, that is also constant, and I, that is the current flowing through each turn, so that is constant one. So B, that is constant, or we can say uniform one. So at any point inside the long solenoid, the magnetic field, that is same one, that is uniform one. Clear to all of you? Now, toroid. So toroid is a hollow circular ring on which large number of turns of the wire are closely wounded. Okay. So it can be viewed as a solenoid which has been bent in a circular shape. Means suppose we have a solenoid and it is bent in a circular shape and end to end it is closed, then we can say it is the toroid. Okay. Now here, suppose as shown in this figure, this one is the toroid and figure B shows the cross section of it. So here, outside the solenoid as well as outside the toroid, the magnetic field, that is 0. Outside means here point P, that is outside the toroid, point Q, that is outside the toroid. So at any such point, the magnetic field, that is 0. Okay. But here inside the toroid, at any point, means in the space inside this wounding, right? The magnetic field, that will be uniform one, constant one. Okay. Now let's derive the equation for this uniform magnetic field in the toroid. Clear? Now equation for magnetic field inside the toroid. Now see, This one is the toroid, and we want to find the magnetic field at any point inside the toroid. So here consider three different Amperian loops. Two are in the exterior part of it and one that is inside the toroid. See, first we think about this Amperian loop 1. Now see, for this Amperian loop 1, the current enclosed by this loop, or we can say current passing through this particular loop, that is 0, because entire current that is outside it. So magnetic field, that is 0. So here in this particular region, at any point, the magnetic field, that is 0. Now, if we consider this third one, this one is the Amperian loop. Now, Amperian loop that is enclosing a surface. So, if we consider the surface, which one is cross section of the toroid, then for this particular loop, see the cursor here. Suppose here the winding that is going inside of that surface, then from other side the winding is coming out, again going inside, coming out. So here if current I is entered to this one, then through each turn we can say current I is flowing. But if we think about the surface enclosed by this Amperian loop 3, then I current enter to the surface, I current leave the surface. I current enter to the surface, I current leave the surface. Now suppose here total number of turns in the toroid, that is capital N. Then total current Ni enter to the surface and total current Ni leave the surface. So net current passing through the surface, that will be again 0. So magnetic field at any point outside this one, that is 0. Clear? So for first Amperian loop, the magnetic field at any point, that is 0. For third one, that is also 0. So in general, now we can say outside the toroid, the magnetic field is 0. Clear? Now consider the Amperian loop 2, which one is represented here by blue dotted line. Now see, here if we consider at any point the direction of the magnetic field, then that is tangential to the loop, and the line element dl, that is also tangential one. So for second Amperian loop, we can write the Ampere's circuital law, integration b dot dl, that is mu 0 sigma I, integration b dot dl, that is integration b dl cos theta. Theta is 0, so cos 0, because b and dl both are tangential to the loop, so in the same direction. That is equal to mu 0 sigma I. Now b is the same one, uniform one, so taken outside the integration. So b integration dl, that is mu 0 sigma I. Now integration dl, that integration we have to carry out over the circumference of the Amperian loop. So that is the 2 pi r, where r is the radius of Amperian loop. So we can write here b into 2 pi r, that is mu 0 sigma I. So here through each turn the current flowing, that is I, and total number of turns, that is capital N. So we can write sigma I, that is Ni. Now take this 2 pi r on right hand side. So here N upon 2 pi r. So total number of tons divided by total length on which these tons are distributed. So that will give you the number of tons per unit length. So here in 2 pi r length, if the total number of tons is n, then per unit length, how much? So with this unitary method, you can understand the number of tons per unit length, that is n upon 2 pi r. So replace this n upon 2 pi r by small n. Again, you will get B equal to mu 0 n I. So toroid, that is nothing but a long solenoid, because when the solenoid is made in the form of circle, end to end it is joined, means now it is endless. Clear? So magnetic field inside it, that is uniform one. Example 4.9. A solenoid of length 0.5 meter has a radius of 1 centimeter and is made up of 500 tons. It carries a current of 5 ampere. What is the magnitude of the magnetic field inside the solenoid? Very simple thing. Length, that is 0.5 meter. Total number of tons in it, that is 500. Current flowing, that is 5 ampere. So number of tons per unit length, that you can calculate by taking the ratio of total number of tons upon total length. So 500 by 0.5, that will give you 1000. Now we have the equation for the magnetic field. B, that is mu 0 n I, where n, that is the number of tons per unit length. આપણે already calculate કર્યા. So substitute the values. Mu 0, that is 4 pi into 10 raised to minus 7. N, that is 1000, so 10 raised to 3. I, that is 5. Solve this one, you will get the answer. Clear to all of you? Then after the topic, that is force between two parallel currents and the definition of ampere current. Now see here, if two conductors which are parallel and both are carrying current, then they exert the magnetic force on each other. Scientist Ampere studied this thing. Okay. Now here we have to derive the equation for the force between two parallel currents, and then we will understand this thing, in which condition they attract each other and in which condition they repel each other. Now see, suppose as shown in the figure, we have two conducting wires A and B, which are parallel to each other and separated by distance D, and both are along the x-axis. Now, the wire A is carrying current IA and wire B is carrying current IB. Okay. Now see here. Suppose first we think about the magnetic field of wire A, which one is carrying current IA at perpendicular distance D from the wire. Then in previous theory, we already studied this thing. Magnetic field of A, that we can write mu 0 IA upon 2 pi D. Now, here, what will be the direction of this magnetic field? So, from right hand thumb rule, we can understand this thing. This magnetic field of wire A at the position of wire B that will be perpendicular to the plane of paper going inside. So here it is represented by crosses. Now we can say this thing here. The situation is this one. The current carrying wire B is in the magnetic field produced by current carrying wire A. And previously we studied this thing. If any current carrying conductor is placed in the magnetic field, the force acts on it. Now see, in the magnetic field of A, the current carrying wire B is placed. So the force on L length of wire B carrying current IB. So here, if we consider length L, then its current element that will be IB into L. And if IB into L is in the magnetic field BA, then the force on it, that is IB cross B, IBL cross BA. Magnitude wise, we can write IBL into BA into sine theta. But IBL, that is in X direction, and your magnetic field BA, that is perpendicular to the plane of paper going inside. So theta is 90. So you can write now force on B by A, that is IB L BA sine 90. So IB L BA, that is mu 0 IA upon 2 pi D sine 90, that is 1. Now we can write therefore force on B by A, that is mu 0 IA IB upon 2 pi D into L. If we take this length L on left hand side, then we will get the force per unit length of the wire. Small FBA, that is capital FBA upon L mu 0 IA IB upon 2 pi D. So if two parallel currents are there, then the force between those currents per unit length of the conductor, that is mu 0 IA IB upon 2 pi D, where D, that is the separation between those two. Clear to all of you? Now here, if we consider the force on B by A, or if we consider force on A by B, no doubt magnitude wise both the forces will be same one, but direction wise it is opposite. Now here in text it is given to you, if the currents are parallel, then there will be the attractive force between those two. And if currents are in opposite direction, anti-parallel, then they will repel each other. Later on, we will prove this thing. Clear to all of you? Now see here, as shown in the figure, this is X direction, this is Y direction. So Z direction, that is perpendicular to the plane of paper and outward, that is Z direction. Now magnetic field of current carrying wire A. So this is wire A, wire B is below it. So if we hold this wire A in the right hand like this, thumb is in the direction of the current, then from the lower side, the fingers are going inside like this. See, from lower side, the fingers are going inside. So here at the position of B, the magnetic field is going inside. So direction is perpendicular to the plane of paper going inside. So that is negative Z direction. That is negative Z direction. So this particular magnetic field produced by current carrying wire A, that is in negative Z direction. So we can represent it in the vector form as vector BA equal to mu 0 IA upon 2 pi D into minus K cap. Now, force on the current element IL in magnetic field BA. So that is F equal to vector IL cross vector BA. Okay. Now, IL, that is in X direction, and your BA, that is in the vector form, this one. So substitute here IL, which is in X direction, that is I caret, cross mu 0 IA upon 2 pi D into minus K caret. Clear up to this one? So we can write now mu 0 IA IB upon 2 pi D into minus I cross K. But I cross K, that is minus J. So we can write mu 0 IA IB upon 2 pi D into bracket minus J cap L as it is. So the force, that is mu 0 IA IB upon 2 pi D J caret into L. So this is the force on B by A. And C, it is in positive Y direction. So wire B is below wire A. And on B, the force that is in upward direction means A is attracting B. So here now we can conclude like this. If the currents are parallel, then they attract each other. So if currents are anti-parallel, then they will repel each other. Clear to all of you? See, the definition of 1 ampere current was given by scientist Ampere using this equation of the force acting per unit length of the parallel or anti-parallel currents in the conductor, which are separated by distance d. See here, suppose first we consider current IA and IB both are 1 ampere. And the separation between those two conductors carrying these currents, that is also 1 meter. And then if we substitute the values here, then current per unit length of the conductor, that is mu 0, 4 pi into 10 raised to minus 7, IA1, IB1 upon 2 pi D, that is 1 meter. And if we solve this one, then we will get the force per unit length, that is 2 into 10 raised to minus 7. Now from this one, this calculation, the definition of 1 ampere current, that is given like this. Now see here, the ampere is the value of that steady current, which when maintained in each of the two very long straight parallel conductors of negligible cross section and placed 1 meter apart in vacuum, would produce on each of these conductors a force equal to 2 into 10 raised to minus 7 Newton per meter of length. Then that is 1 ampere current. Or in other words, we can say if in two long parallel thin wires, the identical currents are maintained, which are separated by 1 meter distance. If the force per unit length of the wire is equal to 2 into 10 raised to minus 7 Newton per meter, then we can say the currents in the wire, that is 1 ampere in each. Clear? Now 1 coulomb charge that we can define in terms of ampere. When a steady current 1 ampere is set up in a conductor, the quantity of the charge that flows through its cross section in 1 second, that is 1 coulomb. Clear to all of you? Example 4.10. The horizontal component of Earth's magnetic field at a certain place is 3 into 10 raised to minus 5 Tesla, and the direction of the field is from the geographic south to the geographic north. A very long straight conductor is carrying a steady current of 1 ampere. What is the force per unit length on it when it is placed on a horizontal table? And the direction of the current is A, east to west, and B, south to north. Now see here. Magnetic field given to you, that is 3 into 10 raised to minus 5 Tesla, and that is in the direction south to north. Current I, that is 1 ampere through the conductor. Now, force on the conductor placed in the magnetic field B, magnitude wise, that we can give F equal to ILB sine theta. Okay. So here first the conductor is placed in east to west direction, means the current that is east to west. Okay. So when current is east to west, your given magnetic field, that is south to north, it implies that the angle between current element and the magnetic field, that is 90 degree. So theta is 90 degrees. So in this particular equation, we can substitute that value F, that is ILB sine 90. Sine 90, that is 1. Now see here, you want force per unit length. So here take length on left hand side. So force upon length will give you force per unit length. Current I, that is 1 ampere. B, that is 3 into 10 raised to minus 5. Sine 91. Solve this one, you will get the answer. Now in second case, when the current is south to north, then in that particular case, your magnetic field and your current element both are in the same direction. So theta, that is 0, and sine 0, 0. So force per unit length of the wire, that will be equal to 0. Clear to all of you? Now torque on a current loop and magnetic dipole. So torque on a rectangular current loop in a uniform magnetic field. Now say here, this one is the schematic diagram for that. In exam, you have to draw this one. This is just for understanding. Okay. See, here two magnetic poles north and south produce the uniform magnetic field in the direction as shown in the figure. And in this particular magnetic field, the rectangular current carrying loop, or we can say coil, is placed. with the dimensions of length and breadth A and B. And suppose current I is passed through it. At present, the loop is placed in the magnetic field in such a way that the plane of the loop is in the plane of magnetic field. So the area vector of the loop. So for any surface, when we represent its area by vector, then its area vector is represented perpendicular to the plane of that particular surface. So we can say the loop is placed in the magnetic field here in such a way that the area vector of the loop is perpendicular to the magnetic field B. Now, let's calculate the forces acting on different sides of this loop. So, if we take the force on this BC side, then BC side, that is with length A, current flowing through it, that is I. So current element, that is IA, it is in the magnetic field B. So force on BC part of the loop, that is IA cross B. But that will be equal to 0. Why? Because IA is parallel to BC here. IA and B both are in the same direction. So theta is 0, sine 0, 0. Similarly, if we think about the force on dA part of the loop, then that is also the current element IA, but here that current element is in the opposite direction of B. It implies that the angle between IA and B, that is pi. So again, this force, that is 0. But now, if we think about the force on this AB and on this CD part of the loop, up to this one clear? Now force on AB part of the loop. So force on AB, say that is F1. So that is IB, B that is the length of AB part. So current element, that is IB. Now it is making an angle 90 degree with respect to magnetic field. Magnetic field, that is in horizontal direction, and IB, that is perpendicular to it in upward direction. So the force on AB part, that is IBB. Similarly, force on CD part, FCD, say that is F2, that is also IBB sine 90, so that is IBB. But the current flowing in AB part and in CD part, that is in mutually opposite direction. In AB, current is flowing in this direction, in CD, downward. So no doubt these two forces are equal in magnitude, but both the forces will be opposite in direction. And here, suppose we consider this type of rectangular loop, then on this particular side, if the force is in this direction, then on this particular side, force will be on this side. So these two forces are in mutually opposite direction and not collinear. These two forces are not acting on the same line. So it will produce the torque. Now, here see, let's represent only those forces. So with respect to reference point that is the center of the loop. Now, force F1 and force F2 are mutually opposite. And the perpendicular distance between those two forces that is equal to side A of the loop. So from the center, both the forces are at perpendicular distance A by 2, A by 2. Now, as per definition, torque tau, that is force into perpendicular distance of force from the reference point. So F1 into A by 2 and another torque produced that is by F2 and that is F2 into A by 2. Now see this, both the forces are producing the torque in such a way that that torque will give the rotation in anti-clockwise direction. It implies that torque produced by force F1 and torque produced by force F2 both give the rotation to the coil in the same direction, and therefore resultant torque, that is the summation of these two torques. Magnitude wise F1 and F2 both are same, IBB into A by 2, A by 2. So half time IBBA plus half time IBBA. So resultantly you will get the torque, that is I into BA into B. But length into breadth of the rectangular coil will give you area of the coil. So we can write the torque tau acting on the current carrying rectangular coil, or in general now we can say on the coil placed in the uniform magnetic field, that is IAB. And in vector form we can write torque tau, that is IA cross B vector. But this I into A, current into area, that is called magnetic moment of the loop. So we can write in vector form torque tau, that is vector magnetic moment into vector B. Direction of magnetic moment, that will be in the direction of area vector. Okay. Now, if your coil or loop that is made by n number of windings, or we can say n number of turns, then very simple, the torque produced will be n times than this one. So here you have to multiply the equation by n. So in that particular case, the magnetic moment, that will be NIA. Clear to all of you? So magnetic moment, that is NIA, its unit, that is ampere into meter square, and its direction, that is in the direction of area vector. And area vector that we have to represent perpendicular to the surface, right? And here we have to fix the direction of area vector again using right hand thumb rule, or we can say right hand screw rule. Okay, we have to place the fingers in the direction of the current and the direction pointed by the thumb, that is the direction of area vector. Clear to all of you? Now, if we take the force on AB, so field that is in horizontal direction here, so we can say, suppose it is in X direction, then In AB, the current is in Y direction. The side AB, that is B. So force F1, that is IBB. Current element and B are perpendicular to each other, so sin 91. Similarly, force on this CD part of the loop, that is also IBB. No doubt magnitude wise this force F1 and F2 both are same one, but the direction of these forces are mutually opposite. As well as these two forces are not collinear. Okay, these two forces are separated by some distance. Okay, there is the separation between these two. Now, when these two forces are not collinear, means it will produce the torque. Now, suppose here we represent these forces in this another figure. So force F1, force F2, these two are in mutually opposite direction. These two are not collinear. And see, the distance between these two forces, that is equal to this side BC and side BC, that is A. So from the center, we can say this portion, that is A by 2, and this particular portion, that is also A by 2. Now from the center of this one, if the area vector, this one, is represented, which is perpendicular to the plane, so perpendicular to this line, and it is making an angle theta with respect to this horizontal magnetic field. So this is the horizontal line. With respect to that, the angle is theta. Now, from the center, the perpendicular distance of force F1. So here, if this angle is theta, then this will be also theta. So perpendicular distance, that is A by 2 sine theta. Similarly, here force F2, that is also at perpendicular distance A by 2 sine theta from the center. So the resultant torque tau, that is equal to F1 into perpendicular distance A by 2 sine theta plus F2 into A by 2 sine theta, because both the torques produced by both the forces give the rotation in the same direction. So here these two torques are sum up. Clear up to this one? So F1 and F2, that is magnitude wise same one, IBB. So we can write here torque tau, that is IBB into A by 2 sine theta plus IBB into A by 2 sine theta. So half time IBB A sine theta plus half time IBB A sine theta. So we will get here torque tau, that is capital I into BA B sine theta, but B into A, that is again area. So tau, that is equal to IAB sine theta. Here again IA, that is magnetic moment. So we can write torque tau in vector form, that is IA cross B. IA, that is magnetic moment, so M cross B. Clear? Now see here, actually this particular theory, if only this one is given to you, then easily you can understand the previous one. See, at present in this theory, the coil is placed in such a way that angle between area vector and magnetic field, that is theta. So we derived this equation. Now the previous theory, that we can easily understand with the help of the special case of this one. In first theory, we discussed this thing. The loop or the coil is placed in such a way that area vector is perpendicular to the magnetic field. So here if you substitute theta 90 sine 91, then torque, that is IAB. In previous theory we discussed that thing here. So easily you can understand from this one also.